So we've got a practice quiz here on this idea of interference. And according to this, we've got two speakers and somebody standing exactly halfway between and hearing no sound at all. Well, almost no sound. What does that suggest is happening at that location where the guy is standing?
Destructive interference.
Yeah. He's hearing almost no sound. That suggests destructive interference at that location. Of course, if he moves to a different location, then he might hear a different kind of interference. But at this location, exactly in the center, he gets destructive interference. And that seems kind of unusual because what would we usually expect exactly halfway between a couple of speakers?
Constructive.
Right. Typically, we'd expect constructive interference because what do we know about how far this wave is traveling and how far this wave is traveling?
It's the same difference.
Yeah.
I mean,
same distance. If we call these, let's say, distance x1 traveled by wave number 1 and distance x2 traveled by wave number 2, it's the same distance. And typically, if waves are absolutely identical and traveling the same distance, that means crest and crest line up, trough and trough line up. So we would expect constructive interference. If we instead get destructive interference, there's got to be something else going on. So what else could be different about these two waves that leads to destructive interference?
Different frequencies.
They might be different frequencies except for two things. First of all, this problem looks like it does specify they have the same unknown frequency.
Oh.
So we don't know what the frequency is, but they're both providing the same frequency. And also, if they were different frequencies, we wouldn't just hear no sound. What very unique interference pattern do we get if you have sources playing different frequencies?
Partial interference?
Not even that. Partial interference or constructive interference or destructive interference, if it's just constant, that's never going to happen from two different frequencies. If you got different frequencies, let me sketch out an example of what the graphs might look like. Let's say we make a couple of time versus y graphs. So let's say this is time versus y graph. And let's say we're listening to two different waves that have different frequencies. What would different frequencies look like on the graph itself? Or how would you be able to tell that they're different frequencies from looking at the graphs of the wave? Yeah, the waves wouldn't match up. And specifically, what about them wouldn't match up? What would you be able to see on a time versus y graph that would tell you that they have different frequencies?
The distance between same points.
Yeah, although keep in mind, this is a time graph, not a position graph.
Oh, wait, never mind.
So instead of wavelength, we would call that?
Period.
Yeah, the waves would have different periods, different amounts of time per cycle. So let's say this is one of the waves with a certain period, a certain amount of time per cycle. And let's say another wave also starts off at a crest, but has a shorter period. It takes less time to complete a full cycle. Something like that. So we can tell from the graph that these waves have different periods and therefore different frequencies. But if we want to check the type of interference, we want to check, do we have crest and crest lining up, or crest and trough lining up, or do we have a crest lining up with a trough? So in this graph, do you have crest and crest lining up, or do you have a crest and trough lining up?
They line up around kind of like the beginning and the end.
Yeah, At this time, at the very beginning, we've got crest and crest lining up. So at that time, what kind of interference is that?
Constructive.
Yeah, which means if these are sound waves, what would you hear if this is constructive interference?
It would be like really loud.
Yeah. So we're going to have a very loud sound at this time. But then if we wait a while, they don't really line up anymore because the periods are different. If we wait long enough, it looks like at this time, the trough almost lines up with, well, maybe not at that time, but at this instant here, it looks like at this instant, one of the waves is equilibrium on the way down, the other one is equilibrium on the way up. Those are exactly opposite types of point in the wave. So what kind of interference is that?
Destructive.
Yeah. So we're going to have destructive interference at this time. You're going to hear very quiet or no sound at all. And close to that, in the in-between region, like in this zone, in between, that would be partial interference. So partial interference means you don't have crest lining up with crest, and you also don't have crest lining up with troughs. So in this period of time, it would be partial interference. And likewise over here, they don't really line up in any meaningful way, so it's just partial again. But then, as you said, by the time we get to the end, we've got like this trough almost lines up with this trough, and it looks like this crest perfectly lines up with this crest. So by the time we get to this time, we're back to constructive again. So it's not really one type of interference the whole time. If the two waves have different frequencies and therefore different periods, you alternate between constructive and partial and destructive and partial and constructive, and then it's going to repeat the same pattern again. So it's going to sound like loud, quiet, loud, quiet, loud, quiet, loud, quiet. And what do we call that phenomenon?
Ringing?
Sorry, what was that?
Ringing? Like when the sound is like ringing in your ears?
Sort of, yeah. It's going to be sort of this wobbling sound. Yeah, this is what we mean by beats.
Oh my gosh.
Beats, I mean, it does sound kind of like a weird ringing, annoying sound. This is sort of I guess you might say the buzzing or wobbly sound caused by two instruments that are a little bit out of tune. But we call this in physics beats. One beat in the sense that there's a sort of a rhythm to the loud, quiet, loud, quiet, loud, quiet, loud, quiet as time passes. We call that cycle from loud to quiet to loud a beat. So that means that as time passes, we're alternating between constructive and destructive instants of time. So we wouldn't really call that constructive the whole time or partial the whole time or destructive the whole time. It's oscillating what type of interference we get. And we would know that's not the case in this situation because we're not hearing beats like this. If they're both providing the same frequency, you don't hear beats, you just hear the same type of interference the whole time. Either constructive the whole time or destructive the whole time or partial the whole time. It might change if you move to a different location because that changes X1 and X2, but it doesn't vary as time passes. Any questions on that so far?
Oh, I have a quick question.
Mm-hmm.
I was wondering, so in the pink area, it's destructive because they're intersecting?
Specifically because we have opposite types of points on the wave. At this point, it looks like one of the waves is equilibrium on the way down, and the other wave is equilibrium on the way up. So those are opposite types on the way down, on the way up, opposite types of points. In fact, if you look close to that, you can tell it's destructive interference because they're canceling out as much as they possibly can. Like near this region, a little bit before that time, let's say, one of the waves has a positive Y value. The other wave has a pretty close to matching negative Y value. So when you add those up, what do you get?
Oh, you get 0.
Right, which means you're going to get essentially a dead zone of time during this amount of time. This period of time is going to have essentially zero loudness because there's no oscillation. So what that would actually look like if we were to draw out the wave, in this region, there would be, this is definitely zero. Let me make that a curve instead of an arrow. We are going to be very at zero here, very close to zero nearby, because the waves almost completely cancel out in that region. Whereas at the beginning, we have a very large crest because crest and crest line up, adding up to a very large crest. Here we get a kind of large, but not as large trough. And then here it looks like they cancel out because we got positive and negative. So it passes through zero. But it looks like we also have passing through zero here, I think, because we've got above and below. So that's going to be passing through zero. Here we've got both positive, but not as much as it could be. They're kind of mismatched. So it's going to be slightly positive. And then it becomes zero for a while here. So what this is going to look like is something like this. Then it just flattens out almost completely here. And then it looks like we have negative and negative. I think it's going to be probably canceling out for more than that, really. And then going to negative. And then passing through zero. Because we've got above and below in equal amounts. And then they're both positive. And then passing through zero here. And then they're both negative, pretty close to matching up. So it's going to be a larger trough. Then both exactly zero, and then a much larger crest. So the actual result is going to look something like this. We get large oscillations representing a loud sound, and then small oscillations, so it's going to be quieter. And then almost completely quiet during this dead zone here. Then quiet, and then louder and louder, and then it's going to repeat that cycle again. So that's the cycle we're talking about when we say beats, going from loud to quiet to loud to quiet to loud to quiet.
Okay, that makes sense. So when it's like really high up on the graph that we just drew, that's high, like high, and even when it's like negative, that's high too.
In terms of loudness, yeah, because loudness is about the amplitude. And if you, I think it might help if we take a look at what's sometimes called the envelope of the wave, which is basically just a curve showing the change in amplitude. Like we start with this amplitude, and then the amplitude gets smaller and down to zero. So if you think of this as like a couple of curves enclosing the wave is oscillating between those values. But then it goes to larger and larger oscillations. So we've got large oscillations going to smaller oscillations to no oscillations, then to small oscillations and then larger oscillations. So these boundaries would be called the wave envelope, in the sense that the wave is contained within those curves. And the larger the wave envelope is, the louder the sound is, because you get large oscillations, that's a loud sound, and smaller oscillations, that's a quiet sound. And then at this pinch point here, no oscillations at all at that time. So that would be zero sound at all. And then back to louder again. So that's what beats look like on a graph. Or if we zoom out a little bit, we might have something like, let me try drawing out more of this. If the wave envelope was something like this, So if these are the boundaries that the wave passes through, the actual wave itself would be large oscillations, then smaller oscillations, then nothing, and then oscillations changing again, and then nothing. Something like this, if that makes sense. So this is this black curve here is the shape I would expect from the total result of two sounds of different frequencies. And that wave is typically called the carrier wave. And that is going to have its own frequency in the sense of number of oscillations per second. Even though the amplitude's changing, you can still look at how much time it takes from crest to crest or trough to trough. So that would be called the carrier period. If you consider how much time it takes from trough to trough on the actual wave itself. So this much time would be called the carrier period. And then the inverse of that would be the carrier frequency, which is the note you would actually hear. But there's also another period going on here. There's another cyclic process. What else is cycling here other than just the individual oscillations? What other process is repeating over and over again here? You've got the individual oscillations of presumably air pressure. That's the period that tells you what note you hear. But also what else is repeating? These beats themselves are repeating, right? We're going from loud to quiet to loud to quiet to loud to quiet. So if you measure the amount of time from loud time to loud time, that's also a period. It's not the period of the wave itself, but it's what we call the beat period. So the carrier period is the time from crest to crest or trough to trough of the actual wave itself, the carrier wave that you actually hear. The beat period is how much time it takes from loud to loud or from quiet to quiet. And those are going to be very different amounts of time. Any questions on the terminology there so far? And have you seen any formulas yet for calculating the beat period versus carrier period? Like for instance, if you knew the frequency produced by the two speakers, let's say, sorry, what was that?
Yeah, we've FB is equivalent to absolute value of F1 minus F2. And then the carrier, it'll be F1 plus F2 over 2.
Yeah. In other words, the difference, or the difference in the average. The beat frequency, which is the inverse of the beat period, that is how many beats you have per second. That's going to be the difference between these. Which in this case, what would be the difference between these two frequencies?
$20.
Yeah, the difference here is 20 hertz. That's the difference between 500 and 520. So you're going to hear a sound that seems to be wobbling between loud and quiet and loud and quiet and loud and quiet 20 times per second. And then the carrier frequency, which is the frequency of the note you actually hear, is the average of those. So what's the average of these two frequencies? Yeah, 510 hertz, halfway in between. So that means you're going to hear a note. You don't really notice the different individual frequencies so much if the notes are very close together in frequency. If the frequencies are pretty close to each other, your ears just hear that as one sound that's the average of those two notes. The average frequency is what you hear as a note, but it's going to be beating 20 times per second. That is 20 oscillations between loud and quiet and loud each second. So that's the general numerical calculations you would be making with beats. The beat frequency is how many cycles per second of loud to quiet to loud, and that's just the difference between the two source frequencies. The carrier frequency is the note, the pitch you actually hear, and that's the average of the two source frequencies. Any other questions on beats so far? And that does count as interference. It's a very unique kind of interference that only happens when the frequencies of the two sources are different. And the really unique thing about that is that it is time dependent. All the other kinds of interference we're going to be looking into, time doesn't matter. It's just the same kind of interference as time passes. But beats, if the frequencies are different, then you get a time dependency, that it matters what time it is, and the type of interference changes as time passes. In that case, nothing else really matters. What we most care about is the fact that it's changing as time passes. Any other questions on beats? All right, then let's go back to the original example when the frequencies were the same. Because we know that if the frequencies are the same, we don't get beats, we just get some type of interference that doesn't change as time passes. So let's investigate that. We have same distance from speaker 1 to this guy and speaker 2 to this guy. So same distance, no difference in path length. But what else could be different that could be causing destructive interference instead of constructive interference? What other aspect of the total phase of the wave could be different? If we take a look at the total phase, the idea of, do you remember all the stuff inside the sine function for the wave equation?
Yeah.
What terms would we need to include for that?
2 pi t over period plus or minus 2 pi x over wavelength plus phi.
Yeah. And we also want to put a delta in front of each of those because what we most care about is not so much what the value of total phase is for each wave. What we care about is the difference between them. So if we apply a delta to each of those terms, let me actually pull that back a little bit. And we can pull the 2 pi out of each delta because 2 pi is just a constant. I would also usually pull time out of the delta because both waves arrive at your ears at the same time. So there's not really any difference in time between the two waves. And I usually think of the divided by period as the same as times frequency. So we've got 2 pi times time times the difference in frequency. But what do we know about the frequencies of these two waves?
They're the same.
Yeah, same frequency, so the difference is 0. In fact, the only time this term matters is when the frequencies are different. And as we were just talking about, that means you get beats and the time term becomes the only really important term because what we would care about is the fact that time is involved. For all the other terms, these terms are time independent. They don't change as time passes. So if the frequencies are the same, you can ignore the time term and everything else will be just a single value for all of time. Unless, of course, you change the situation by moving around or something. Also, what do we know about the wavelength of both of these speakers? That's also the same, yeah, because the wavelength and speed or wavelength and frequency are related by the speed equation. Speed equals wavelength times frequency. So if they're the same frequency, and of course they're in the same medium, so they have the same speed, then they've got to be the same wavelength as well. So we can take this equation and the lambda can be factored out of the delta because any constant can be pulled out of a delta. We've got x1 over lambda minus x2 over the same lambda. It's the same lambda, so we can factor it out. However, in this case, what do we know about the distance traveled by one wave and the distance traveled by the other wave?
Same distance.
Right, which means delta x would be 0, so that term's gone also. The only way you can have it, the only other thing that could be different about these waves is what?
The phase constant.
Yeah, they could have different phase constants. In fact, in this case, since everything else is the same, the difference in phase constant is the difference in total phase. There is no other difference. Any questions on that so far?
I have one question. I was wondering, did the plus and minus matter in this case?
Yes, it does. In fact, what is the in the original wave equation? What does the plus and minus signify?
If you're going to the left or the right.
In a one-dimensional wave, yeah, whether you're going in the positive x direction to the right or the negative x direction to the left. If we're talking about a 2- or 3-dimensional wave, though, left and right don't really matter so much. It's more about, is the wave spreading out from the source or is the wave collapsing towards the source? So what's happening in a typical sound wave from a speaker? Is the sound wave going away from the source or towards the source?
It would go away from the source.
Yeah. Typically, if you've got a single point creating a single point source creating a wave, that wave is spreading out from the source. The only way you'd have a wave collapsing in towards a single point is if you've got something like a room that's lined with speakers and they're all blasting the same pulse towards the center. So for any single point source, the wave is always spreading out away from the source. We treat that as moving in the positive direction because it's increasing distance from the source. And positive direction of travel means we use a negative here. So typically for any 2- or 3-dimensional wave, that's going to be a negative. Any other questions on that so far?
In terms of wave direction, I was doing one of the practice quizzes and they gave us, it was a one-dimensional wave and they gave us the sign and it was a negative. And then they told us to graph in the next part of the problem. So I thought, oh, it's moving to the right. But then the explanation said the wave was moving to the left.
It had a minus the x term in the equation?
Yeah.
If the x term is being subtracted, then that should be moving to the right, the positive x direction.
Yeah, that's what I thought.
Maybe we can take a look at that later, because that seems like a discrepancy there. But let's finish this one up while we're at it. Yeah, go ahead and send me that practice quiz. I'll take a look at it later.
Okay.
In this case, though, it says he hears almost no sound, so we should expect destructive interference. What has to be true about the total difference in phase, delta capital phi, in order to have destructive interference? If you want waves to be destructive, how offset would you expect them to be? For example, if you have like, let's say you've got this wave, and let's say you've got another wave that's absolutely identical. If they're completely identical, what kind of interference is that? Yeah, that's constructive. If we shift it so they're offset, though, Now what kind of interference is that? Yeah, that's still going to be constructive, right? We need a half of a cycle to be destructive. If we have these waves that sync up perfectly, but we shift it by exactly half of a cycle, that's now destructive. Or a whole cycle, and it should now be constructive. I just haven't really drawn this perfectly the same. Or if we take 1.5 cycles, we're back to destructive again. Or 2 cycles, we're back to constructive again. So in general, to get constructive, you need to be offset by a whole number of cycles. To be destructive, you need to be offset by something and a half cycles. So constructive needs to be a whole number of cycles offset. Not necessarily a whole number of wavelengths specifically, but a whole number of cycles in total. And we're talking about a radian measure here. So in radian measure, what's one full cycle?
2 pi.
Right. So constructive interference would mean the total phase difference must be a whole number times 2 pi. That whole number, let's just call that n. So some whole number n times 2 pi. But if we combine the 2 and the n, what kind of a number is 2n going to be? If you take any whole number and multiply by 2, what category of number is the result going to be?
Even.
Yeah. So a useful way to think about this is an even number times pi. Not that there's anything particularly special about even numbers in this context. We're looking for a whole number of cycles. But since a cycle is 2 pi, a whole number of cycles works out to any even number times pi. And that could be positive or negative. Whereas something and a half cycles would be something and a half times 2 pi. If you multiply that out though, multiplying the 2 times the n and the 2 times the 1/2, you get 2n plus 1 pi. And what kind of a number is 2n plus 1?
Odd.
Right. Again, nothing particularly special about odd numbers in this context. It's just that something and a half times 2 pi will always work out to an odd number times pi. So in general, if you find the delta total phase, all these delta terms added together, if there are more than one, if that works out to an even multiple of pi, that suggests constructive interference. An odd multiple of pi would be something and a half cycles. So that would be destructive interference. And then anywhere in between, like if you get 3.7 pi or negative 2.5 pi or something, that's neither even nor odd. So that would be just partial interference. Anything other than these categories would be partial. Any questions on that so far?
Oh, can you just clarify? So for the argument, like the one that's inside of the sign equation, what's the difference between what it's equal to and like the one inside, I guess?
This one?
Like the delta phase constant. Yeah. Like
well, the y equals all this stuff. If y equals a function of x and t, this is describing the graph of the whole wave. So it's describing, the y value is describing what's the displacement, how high or low the wave is at some position and some time. But if you look at just what's inside the sine function, that's an angle. Like if you actually calculate that, you might get maybe 3 pi over 4 or something in radians. So you'd be taking amplitude times sine of 3 pi over 4. That radian measure tells you which part of the wave you're at right now, whether you're at a crest or a trough or an equilibrium or somewhere in between. For instance, if everything inside the sine function is pi over 2, sine of pi over 2 is 1, which is the highest it can go. So if everything inside the sine function is pi over 2, you're at a crest. If it's 3 pi over 2, you're at a trough. If it's 5 pi over 2, you're at another crest again. So when we're taking the total phase difference, when we're subtracting the stuff inside the sine function from one wave minus the stuff inside the sine function from the other wave, we're looking at whether there's any difference in what type of point we're at. If that difference in total phase is 0, that means there's no difference in the type of point. They're both crests or both troughs or whatever. So you're at constructive interference. If the difference is pi, that means like one of the waves is half a cycle ahead of the other, so it matches up with the next trough. So that would be something like this, if they're offset by pi, half a cycle. And that leads to destructive interference. But if the difference is 2 pi, that's 2 whole cycles offset. So they line up again, and you get constructive interference. And that's where this idea of a whole number of cycles versus something and a half cycles comes in. Any other questions on that so far? So that's really the main difference here. The wave equation, y equals amplitude times sine of all this stuff, that's describing the displacement at any point on the wave at any time. The total phase equation is talking about what type of point are you at? Are you at a crest or a trough or somewhere in between? And in particular, the total phase difference, which what we really care about, this equation here. The total phase difference is talking about, is there any difference between what type of point you're experiencing from both waves? If there's no difference, or if the difference is a whole number of cycles, then that means you get crest and crest at the same time, trough and trough at the same time. So that's constructive interference. If the difference is something and a half cycles, you get destructive interference from a crest and trough canceling out. Any other questions on that? So if this guy is hearing destructive interference in the middle, what does that tell you about the difference in total phase?
It's an odd multiple of pi.
Yeah. Delta total phase, difference in total phase has to be an odd multiple of pi because they have to cancel out. And we have some degree of freedom for choosing this here. What would be the easiest odd multiple of pi to use?
3 pi over 2.
That's not an odd multiple of pi though. That's a fraction.
Oh wait, sorry.
What's the easiest odd number? Yeah, if we just have 1 pi. So if you just have, if the only information you have is this location leads to destructive interference, the simplest way to deal with that would be to set delta total phase equal to 1 pi. And that means delta little phi has to be pi because everything else is 0. There's no difference in frequency. There's no difference in path length. So the only thing contributing to the total phase here is the difference in little phi, the phase constant. What that tells us is that the 2 waves have to have different phase constants. One of those speakers is producing a wave with a certain phase constant. The other wave is producing another speaker is producing a wave with a different phase constant. And the difference between them has to be pi, or any odd multiple of pi really, but we can just use pi as the difference. Any questions on that so far? And this is often something to look for if you've got a situation that you would expect to be constructive just because of the distances involved, like the exact center between 2 speakers. I would usually expect that to be constructive. But if it's destructive instead, that's presumably because of a difference in phase constant. So delta little phi, lowercase phi, is going to be pi. So we'd say one of the waves, one of the speakers is ahead of the other by half a cycle. And what would that mean about the actual behavior of the speakers? What does it mean for the phase constants to be different by half a cycle? Do you know what's going on inside a typical speaker to create the sound in the first place? In a typical speaker, you've got a thin membrane, usually called the diaphragm, that's attached to a small motor that pushes back and forth. When it pushes, it's creating a high pressure zone of air. When it pulls, it's creating a low pressure zone of air. So as the membrane pushes and pulls, it's creating a crest, a trough, a crest, a trough with high pressure or low pressure air. If the speakers are synchronized with each other, if they're both pushing at the same time, both pulling at the same time, they both create a crest and both create a trough at the same time. What would that suggest about their phase constants?
They're the same.
Right, same phase constant. So in that case, we would describe the speakers as in phase with each other. If the speakers are in phase, they're both creating a crest, both creating a trough at the same time. So there's no difference in phase constant. And for electrical speakers, what typically causes that is if they are wired the same way. Like if you plug in positive and negative wires into the positive and negative terminals of one speaker and plug in the other speaker exactly the same way. Then they're going to be synchronized with each other. But if you unplug the wires from one speaker, swap positive and negative and plug them back in, those are now wired oppositely, which means one of those speakers is going to be pulling when it should push and pushing when it should pull. So if they're exactly offset, pushing instead of pulling and pulling instead of pushing, then one creates a crest when the other creates a trough. So what would be the difference in phase constant there? If they're offset by how far apart are a crest versus a trough in one cycle? What fraction of a cycle is that?
Half, so it would be like 1 pi.
Exactly. If the speakers are offset by exactly half a cycle due to being wired oppositely, they're half a cycle out of phase, we would say the phase difference is 1 pi. So it seems that's what's going on here. The speakers are wired oppositely, I would say, as the description, if we wanted to describe what's causing this. So half a cycle offset is why you get destructive interference in the middle. But then if you move to a different location, like let's say you move to this location, what difference would that make? Why would that cause changes to the total phase equation?
Because you're not exactly half a cycle apart anymore. So
well, the delta phase constant, those are just referring to the speakers. The speakers are still wired the same way. You haven't changed the speakers. You've just moved from where you were standing and walked over to a new location.
oh, is
You
it
haven't
a
changed the speakers.
path length difference?
Yeah, we're changing the path length. Instead of one of the waves traveling 4 meters and the other wave traveling 4 meters, now one of the waves is traveling a shorter distance and the other wave is traveling a longer distance to get to your location. So that means there will be a delta X term in that case. There will still be the same delta phi term because we haven't changed the speakers at all. So delta little phi, the difference in phase constant, will still be 1 pi or whatever it was in the beginning. But the delta X term will now be non-zero. There will be a difference in path length, which we could calculate as x2 minus x1 or x1 minus x2. You just want to choose an order of subtraction and be consistent with it. Any questions on that?
Oh, just for like that, the annotation, I guess. There's like a little phi and then a big one. So when you wrote the equation for the total phase, are those two the same? Or are
they unfortunately look kind of similar in this font, but they are different. Specifically, we have a lowercase phi here. Let me make a note of that. Lowercase phi is the phase constant. And that's a value associated, a constant value associated with each wave. And that essentially represents what's going on at the source. Like the phase constants being the same or different tells you, are the speakers themselves synchronized or non-synchronized? Whereas the total phase, capital phi, is talking about the combination of everything going on. The phase constant difference and path length difference and frequency difference if there is one. So the capital phi is the total phase, which is a combination of all of these effects together. So lowercase phi, the phase constant, is talking about the sources of the waves and whether they're in sync or not. Capital phi, the total phase, is talking about that and the path length difference and the frequency difference, if there is one, all unified together or all added up. And the total phase is what matters for type of interference. Any other questions on that? All right, then try this approach on some of the other examples. If you have any practice quizzes or other problems from the FNTs, let me know if you have any other questions, and I will see you next time.